Continuing on, let's try and look at a different model of a DC motor, or look at a DC motor from a different viewpoint. Let's try and generate a static model of the DC motor, or a model of the DC motor when it's in steady state. So thinking back to the previous slides, we found that the differential equation describing the electrical dynamics of the motor had this form. And so think about how this might change once we're in steady state. So you can imagine that the motor is just sitting there. We apply a voltage to it. The current through the motor changes. The speed of the motor changes. And eventually it reaches some steady state speed. So once it reaches that steady state speed, how does this equation change? Well, basically, since the current isn't changing anymore, the current through the circuit is constant, its time derivative is 0. And so this differential equation becomes the following. The relationship for motor torque is still equal to the motor torque constant times the armature current. If we solve for the armature current, we get that it's equal to T divided by K. And if we take that expression and substitute it into the first equation, we get the following. And this equation gives us a relationship between motor speed and motor torque in steady state. Let's go ahead and rearrange it to solve for T. So I'm going to go ahead and take this negative term with the torque in it, add it to the right hand side. Then to solve for T, I'll multiply through by K, and I'll divide through by R sub A. If I do that, I get the following. So I move that to the right hand side, multiply through by K to cancel that. I get a K there and a K there. Divide through by RA to cancel that. I get a division by RA, a division by RA. If you look at this, you can see that the torque is a linear function of the motor speed. This is a constant. The motor torque, the back EMF constant, and the armature resistance are all constants. And then for a given applied voltage, this is also a constant. So it sort of has the form Y equals mx plus b, where the torque is the dependent variable and the speed is the independent variable. And so we get a straight line relationship between torque and speed. Looking at this, the constant multiplying the independent variable is our slope. And it's constant and it's always negative because these parameters are positive and there's a negative sign in front. So we get this constant slope that slopes downwards. And this is a function of these parameters. We also get that the intercept, the y-intercept, changes as we change the voltage applied to the motor. So you can see when we have one armature voltage, we get this line. We apply a different armature voltage, we get a different y-intercept. And so this is an alternative sort of model of a DC motor. Such a thing, a torque speed curve like this, can be used for sizing a motor. It can even be used for control in some instances, but you lose some elements of the motor's behavior, its transient response. But in some instances, this may be sufficient. In practice, the maximum torque of a motor is usually limited. And the reason that that is done is because at high torques you have high currents, and that can damage the motor if you do it for a sustained amount of time. In many cases, you may allow the motor to momentarily have a very high torque, but usually the control system will limit it so that it's not for a sustained amount of time, because that will cause damage to the motor. Here's another modeling example with a DC motor. So here we have a DC motor with an armature circuit and rotor inertia J sub 1 and friction B sub m. And the output of the motor is connected to another inertia, a load inertia J sub 2, via a flexible shaft with stiffness K and damping B. And we want to write the equations of motion. So this one will provide a good refresher on the modeling of mechanical systems. Before we begin, let's just take a second and think about how many equations of motion we need to completely model the dynamics of this system. It turns out we're going to need 3 equations. One equation for the electrical circuit and one each for the 2 rotational inertias. Starting off, we'll generate the equation of motion for the electrical part of the system, the circuit. So we have a voltage source, E sub A, then the rotor or armature has some resistance, some inductance, and then some back EMF. So again, recall that we can model this using Kirchhoff's voltage law, Kirchhoff's loop law, where we will assume that the armature current flows clockwise. So starting at this point of the circuit, moving in the direction that the armature current is flowing, we'll initially have a bump in voltage due to the voltage source. Then we'll have a drop across the resistor, where the drop is equal to the product of the current and the resistance according to Ohm's law. Then we'll have the drop across the inductor, where the voltage across the inductor is proportional to the time rate of change of the current. And then we'll have the drop due to the back EMF, because the polarity of the back EMF opposes the polarity of the supply voltage. At that point, we're back to where we started, and so the total change in voltage around the loop is 0. If I just go ahead and quickly rewrite this and substitute for back EMF, where I know that the back EMF is equal to the back EMF constant times the rotational speed of the rotor. This gives us the first of the 3 differential equations that we need to describe the motion of this system. Moving to the next slide, we'll now go ahead and generate the equations of motion for the mechanical portion of this system. And so in this case, we have the inertia of the motor, the rotor, and it's connected via a rotational spring and a rotational damper to the other inertia, J sub 2. We've defined, if you look at the previous slide, the direction of positive angular motion. So theta sub 2 is positive in that direction, where theta sub 2 is the motion of J sub 2, and theta sub 1 is the motion of the inertia of the rotor, where it's positive in the same direction. And then we also make the presumption that the motor has some friction, where the viscous friction coefficient is given as B sub m. So in order to model this system, we can draw the free body diagram for each of the 2 inertias. We'll have inertia 1, J sub 1, where theta sub 1 is positive in that direction. the torque that's generated by the motor that's applied to the rotor we'll presume is positive in the direction of positive theta 1. The frictional torque is going to oppose the rotation of the motor. So we can imagine some frictional torque, and we will model it as being proportional to the speed. The torque itself is proportional to the armature current. In addition to the motor torque T and the frictional torque, we will also have torques applied to the inertia due to the spring and the damper. And so again, this is a good review. And so the way that I usually determine the orientation of the spring torque is that I hold the second mass or inertia still, and I move the first inertia in the direction of positive motion. So if I move this inertia in the direction of positive theta 1, I will twist the spring, and the spring will want to spring back. So I can imagine that I'll have a TS in that direction. And the magnitude of the torque is proportional to the deformation of the spring. So it has some stiffness K, some spring constant K, and the amount of twist is equal to how much the one end moves minus how much the other end moves. Similarly, we'll also have a torque due to the damping in the shaft, except here the torque is proportional to the relative speeds, the difference in the relative speeds of the two ends of the damper. So this is the free body diagram for J sub 1. You can also draw a free body diagram for J sub 2, where theta 2 is positive in the same direction as theta 1 is positive. And I can do the same sort of process where I could hold J1 still, move J2 in the direction of positive theta 2, imagine the spring twisting and then wanting to spring back. The alternative to that is to just draw the torques as being equal and opposite to the torques applied to the other inertia. So you can imagine that if you took this spring and you twisted it, the torque generated on the two ends would be equal and opposite. So you could imagine that T sub S and T sub D are equal and opposite the application on J sub 1. And this direction, as I've defined it, presumes that T sub S is defined in this manner, where the ordering is theta 1 minus theta 2. If I switch the order of theta 2 and theta 1, then the torques would be positive in the opposite direction. Once we've drawn the free body diagrams, we can then go ahead and generate the equations of motion. So we'll do it first for inertia 1, and we will apply Newton's laws or Euler's laws, where we have that the sum of the moments is equal to J alpha. So in this case, we have torque T in the direction of positive theta 1, so it is also positive. We have the frictional torque in the opposite direction, and then we also have the spring torque and the damper torque in the opposite direction. And it's equal to J times angular acceleration, where the rotational inertia in this case is J sub 1, and the angular acceleration is theta 1 double dot. And then we can substitute in the different expressions we have for the different torques. So we have the motor torque is equal to the motor torque constant times the armature current. Subtract the frictional torque, where we're actually given that the viscous frictional coefficient is B sub m. B sub m, theta 1 dot. Then we have the torque due to the spring, which is K, times theta 1 minus theta 2, minus the torque due to the damper, which is B, times theta 1 dot, minus theta 2 dot, and that's equal to J1 theta 1 double dot. So this is our second differential equation for the equation of motion. And then finally, we have the equation of motion for the second inertia, where again it's sum of the moments equals J alpha. In this case, the only two torques that we have acting on the inertia are the spring torque and the damper torque. They're both pointing in the direction of positive theta 2, so they're both positive. The inertia in this case is J sub 2, and the angular acceleration for this inertia is theta sub 2 double dot. Substituting in expressions for T sub s, we have K times the quantity theta 1 minus theta 2. Substituting for T sub d, we have B times the quantity theta 1 dot minus theta 2 dot, and that's all equal to J2 times theta 2 double dot. And so this gives us our final and third differential equation needed for modeling this system. If you think back, one quick and dirty way for us to give some confidence that we've oriented our torques in the right direction is to look at the signs on our variables. So in these sorts of systems, all of the theta 1 terms should have the same sign, and all of the theta 2 terms should have the same sign. So here, if I distribute this negative k, this becomes positive. If I distribute this negative b, this becomes positive. So all the theta 2 terms in this equation are positive. If I add all of these negative theta 1 terms, negative, 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 to the right-hand side, then the theta 1 double dot, the theta 1 dot, and the theta 1 terms are all positive. And so we have the same signs, and this is a good check. Same thing with equation number 3. K theta 1 is positive, B theta 1 dot is positive. If I add negative K theta 2 to the right-hand side and negative B theta 2 dot to the right-hand side, then all the theta 2 terms are positive.